Hey everyone, and welcome. Have you ever stood in your kitchen and wondered what really makes olive oil a liquid and butter a solid? I mean, they're both fats, right? We hear all the time that some fats are good for you and others are bad, but the why behind it all usually stays a mystery. Well, today we're going to crack that code. We're going right down to the molecular level to see how the science of fats plays out on our menus. So let's start with that fundamental question. You see it every day. At room temperature, butter is solid. You can spread it on toast. Olive oil? It's a liquid you pour into a pan. Now, this isn't just a random fluke of nature. It's actually all about physics, and it's rooted deep, deep down in their molecular structure. And, as you're about to see, understanding this one simple difference has huge implications for our health. Okay, so to solve the solid versus liquid mystery, we need to dive into the science of melting. Turns out it all boils down to one single key property that basically acts like a master switch for every fat out there. And that property is called the melting temperature, or just TM for short. You can think of it as a fat's own personal thermostat. It is the exact temperature where that fat stops being a rigid, ordered solid and becomes a free-flowing, disordered liquid. Every single fat has its own unique melting temperature. This visual here does a great job of showing what's going on. When a fat is below its melting temperature, its molecules are packed together super tightly, kind of like soldiers standing in a perfect formation. That's your solid state. But once you add enough heat to cross that melting point, that energy just breaks those formations apart. The molecules get all disordered and start moving around freely, and voila, you've got a liquid. It's as simple as that. So the obvious next question is, what decides that melting point? Why is butter so high that it's solid at room temp, while olive oils is so low? Well, the answer is hidden in their molecular blueprint. And it has everything to do with something I like to call the power of the kink. You see, there are really two main things on that blueprint that determine a fat's destiny. The first is its chain length, basically how long the molecule is. And the second, and this one is the real game changer, is its degree of unsaturation. That's all about whether or not it has any double bonds that literally put a bend or a kink in its shape. Let's break them both down. First up, chain length. And honestly, the logic here is pretty straightforward. The longer the fatty acid chain, the more surface area it has to stick to its neighbors. They just pack together more neatly and tightly, kind of like stacking long logs. It's a strong structure. Shorter chains, they're more like small branches. They just don't stack as well. And you can see the result right here. Longer 18-carbon chains need way more heat, 55 degrees Celsius, to melt compared to the shorter 14-carbon ones, which turn to liquid at just 24 degrees. But this is where things get really fascinating. It's the shape of the molecule. Saturated fats, as you can see, are perfectly straight. They're like little molecular bricks that can stack together perfectly. But a unsaturated fat? It has a double bond that creates this really obvious kink in the chain, making it totally impossible to pack neatly. And then you have trans fats. They're the weird ones. They have a double bond, but their structure is still pretty straight, which has some really important consequences, as we're about to find out. And just look at how dramatic this tiny difference in shape is. We're looking at two fats here. Both are 18 carbons long, exactly the same length. The only difference between them is that stearic acid is straight and oleic acid has just one of those kinks. Now check out their melting points. The straight one, stearic acid, needs almost 70 degrees Celsius to melt. The kinked one, it melts at just 13 degrees. That is a massive difference. Let that sink in for a second. A single, tiny bend in the molecule, one little kink in its architecture, causes its melting point to plummet by over 50 degrees Celsius. That, right there, is the power of the kink. And it's not just some number on a chart. It's the entire reason olive oil is a liquid in your kitchen and the fat on a steak is solid. It's a huge, real-world effect that comes from a tiny, invisible change. Okay, so this is all really cool science, right? But what does it have to do with us? Why should we care about this beyond just what's happening in our kitchen? Well, this is where it all comes together. This is where we connect that abstract molecular shape directly to our own bodies and our health. It's because the exact same properties we just talked about, the shape, how well it packs, its melting temperature, those are precisely what determine how a fat behaves inside our bodies. This isn't just theory. It directly explains why some fats are literally essential for us to live and why others are linked to disease. So let's start with those kinked fats. It turns out some of them are what we call essential fatty acids. That means our bodies absolutely have to have them to function, but we can't make them ourselves. Why not? Well, our cells just don't have the right tools, the right enzymes, to create that double bond, that kink, past a certain point on the chain. We simply can't do it. So we have to get these essential fats, like linoleate, from the food we eat. They're crucial building blocks for all sorts of important things in our bodies. Now, on the flip side, you've got the straight fats, the saturated and trans fats. Remember their superpower. They can pack together incredibly tightly, which gives them those high melting points. Well, inside our bodies, that superpower can become a real problem. That very same tendency to pack together into these rigid, ordered structures is linked to health problems like atherosclerosis, where these fats can actually contribute to forming hard, rigid plaque inside our arteries. All right, let's put all the pieces together now. We can take everything we've just learned and build one clear, complete picture, a simple guide to really understanding the fats on your plate. This chart just lays it all out perfectly. First up, saturated fats. They're straight, so they pack really well, giving them a high melting point. The advice? We should limit these. Then you have the cis-unsaturated fats. They're kinked, so they can't pack well, giving them a low melting point. These are the ones that can be essential for us. And finally, trans fats. They're pretty straight, so they pack well, have a high melting point, and these are the ones we really want to avoid. You see that connection? It's a clear, logical line that goes right from the molecule's shape to its impact on our health. So if there's one thing you take away from all this, let it be this fundamental principle of all biology: structure defines function. And dietary fats are the perfect example. That simple molecular architecture, how long a chain is and whether it has a simple kink, that dictates everything. It determines if a fat is a solid or a liquid in your kitchen, it determines its job inside your cells, and ultimately it determines its impact on your health. So the next time you look at a food label and see saturated or unsaturated, you're not just seeing words anymore, you're seeing architecture. And now you know how to read the blueprint.